What's up, guys? Welcome back to the 12 ISLs of Christmas. Today, we're going to be looking at our final combinatorics problem of the series, and this is a problem from 2008. It's 2008 C4, and it actually appeared on the IMO that year. This is 2008 IMO problem 5. And here's the problem. Let n and k be positive integers with k greater than or equal to n, and k minus n an even number. We have 2n lamps labeled 1 through 2n, and each one is either on or off. Initially, all the lamps are off, and we consider sequences of steps. At each step, one of the lamps is switched from on to off or from off to on. So we have a bunch of lamps here. So in the case where n equals 3, we have 6 lamps. And this is 1, 2, 3, 4, 5, 6. Let n be the number of such sequences consisting of k steps, and resulting in the state where lamps 1 through n are all on, and lamps n plus 1 through 2n are all off. So we want to somehow flick these first 3 guys on, and the last 3 guys off. And in the case where k equals 7, for instance, one way we could do this is, and I'm labeling the steps here, it's 1, 2, 3, 4, 5, and then 6 and 7. And that makes each of these guys on and each of these guys off. So that's n. And m is the number of such sequences where this is still true, but none of the lamps n plus 1 through 2n are ever switched on. And that means that our state from earlier, this does never work. Like, we can't do that. So we have to move them somewhere else. And we want to find out the ratio between n and m. So how can we get started on this problem? Well, one thing to note is that k minus n is an even number. And it's important why this should be given. Because if k and n are of different parity, then we cannot get to n light switched on. Because suppose that we have k equals 4 in this case. Then we switch this light on, then we can switch it off or switch another one on, which gives a total of 2 lights on. And then we can get 3 or 1 light on, and so on and so forth. And in general, we have that after 4 switches, after 4 flicks, we have that an even number of lights are on. And that's bad since n is odd. And we have an even number of lights on because we're basically just changing the parity. Like, if we think of each of these guys as numbers, such as like 0 or like 1, 0, 0, 0, 0, 0, in the case where 1 is on and 0 is off, then switching a light from on to off or off to on changes it from 0 to 1, and therefore affects the parity of the sum of these guys. And similarly, changing it from 1 to 0 also does the same thing. And therefore, the parity always changes on every step, so when k equals 4, the parity is even when it should be odd. So that explains why k minus n must be even, because otherwise n and m are both 0, and we can't divide 0 by 0. But looking at this k minus n idea motivates us to look at this binary type of thing. So we want to switch these guys off. We want to flick these guys an odd number of times. So we have odd, 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 no, and then even, 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 because we want to flick these last guys an even number of times. So how can we do this? Well, we can try expressing this as a sum, because we can let a1 be the number of times we flick this switch, a2 be the number of times we flick this switch, and so on and so forth, until we get to a2n. And when we compute the sum, we want to find the sum of all numbers such that a1 plus a2 plus all the way to plus a2n is equal to the number of total flicks, which is equal to k, but also a1, a2, all the way to an are odd, and an plus 1 all the way to a2n are even. So those are our constraints on the sum. And what exactly are we summing? Well, we want to apply each of these steps in some order. And there are k total steps, and we have a1 steps of type 1, a2 steps of type 2, and so on and so forth. And if you're familiar with multinomials, then this is just equal to k choose a1, a2, all the way to a2n. And basically this means that it's k factorial over a1 factorial, a2 factorial, all the way to a2n factorial. And the way this works is that basically you just order the k steps in any order, giving k factorial on top, but then we must divide for overcounting because the a1 moves of type 1 are the same. And we must divide by a1 factorial for that. And we continue going and dividing. Anyways, so this is equal to n. And we need to somehow evaluate this nasty sum. At this point, we need to somehow evaluate the sum. And for those of you who are comfortable with working out these multinomial sums, it's not super hard to see where to go from here. However, if you're new to this type of idea, then this will feel like a huge leap of faith for you. Now, in general, when we have these type of weird multinomial sums, a good idea is to consider the generating function. And here, when I mean by generating function, I mean by some function f of x1, x2, all the way to x sub 2n. And we're dealing with 2n variables here because we have 2n lights. And we need to somehow find a generating function that somehow encodes these multinomials. And one such generating function that does so is f of x1, x2, all the way to x2n is equal to x1 plus x2 plus all the way to plus x2n, all the way to the power of k. And indeed, if we're looking at a coefficient of x to the a1, x1 to the a1, x2 to the a2, and so on and so forth, then we need this multinomial coefficient in front of it. So that means that the coefficients in the expansion of this are simply these multinomial coefficients. However, we have all of this extra information here. And we need to somehow encode this inside our generating function. And this is where another key idea regarding generating functions appears. And again, this feels like a huge leap of faith. So consider what happens when we take f of x1, x2, all the way to x2n, minus f of negative x1, x2, all the way to x2n, and divided by 2. And here, let's consider the powers of x. If the power of x1 is even, like if it's 0, then these guys are the same. And if the power of x1 is odd, then these guys are inverses of each other. So that means that it's just 2 times that term. So all in all, this is equal to the terms of f with x1 power odd. So we can weed out all of the odd powered x1 terms here. And this gives us a1 is odd. So we can continue weeding out terms in this way. And by the way, this technique here is a special case of what is known as the roots of unity filter. And basically what we're doing here is that we're using the roots of unity to weed out special values in the exponent of x1. And we can similarly do things for x2 and all the way to xn, which we will do. So I've made a bit more space on this board so that we have more room to carry out our computations. So as I said earlier, this is the concept of the roots of unity filter. So let's apply it to x2 now. So when we apply it to this term here, we get that f of x1, x2 all the way to x2n minus f of x1 negative x2 all the way to x2n all over 2 minus f of negative x1 x2 all the way to x2n minus f of negative x1 negative x2 all the way to x2n all over 2 and all that over 2. And this is equal to f of x1 x2 all the way to x2n minus f of negative x1 minus x1 x2 x3 all the way to x2n, and then minus f of x1 negative x2 all the way to x2n, and plus f of negative x1 negative x2 and all the way to x2n all over 4. And this is where all terms have x1 to the a1, x2 to the a2, where a1, a2 are odd. So even though we have this really nasty expression, we can still somewhat see a bit of a pattern here. When we have only one negative sign, we have that the sign is minus here. But when we have two negative signs or 0 inside, then it is just positive. And this suggests that when we have all of the x1 through xn conquered, then the sign is just negative 1 to the power of the number of negative signs in here. And this is actually not hard to see why, because every single time we have a minus sign here, and every single time we're adding one, we negate the term. And every single time we negate it, two negations make it positive. So that means that when we have an even number of negative signs in here, we get a positive. Okay, so this is what we have so far. We have each of the bi represent a positive or negative sign, and at b1, x1 represents x1 or negative x1, depending. And we multiply by b1 because that way we can get rid of the even coefficients, as explained earlier. And we have similar things for each of these guys. And this represents x1 to the a1, x2 to the a2, all the way to xn to the an, where all of these guys are odd. And also we must still be careful because we need to divide this by 2 to the n, because remember how we keep dividing by 2 every single time. But now we need to somehow deal with the fact that the power of these guys must be even, because those lights are off. And this gives a variant of the roots of unity idea. Instead of looking at odd powers, how come we can't look at even exponents? Because can we just change our approach slightly? Yes, we can. Because f of x1, x2, all the way to x2n, and then this time we change the sign to plus f of x1, x2, all the way to negative x2n, all over 2. that eliminates all of the odd exponents because then each of these guys are just the inverses of each other. And when we have that the exponent is even, then they're the same. And therefore, we get that this contributes even powers. So we can further update this to a sum as follows. So let me go ahead and erase this. And I'm going to rewrite it in a bit. So we have b all the way to b2n, b1, b2 all the way to b2n in negative 1, 1. And we still have these factors here since we're not introducing any minus signs with the xn plus 1 all the way to x2n. But we do have bn plus 1, xn plus 1, all the way to b2n x2n. And when we let x1 equals x2 equals all the way to equals x2n equals 1, this gives us a sum of all of the coefficients. And we want this to happen because now this has x1 to the a1, x2 to the a2, all the way to x2n to the a2n, where all the ai satisfy our requested properties. And this has the coefficient of k a1 all the way to a2n, which is what we need. So we can just get rid of these guys entirely and just sum them all by plugging in x1 equals x2 equals all the way to x2n. So we have an expression like this for n. And we recall we must divide by 2 to the 2n, since we're dividing by 2 on every single step. And when we plug in the definition of f, we get that this is b1 plus b2 plus all the way to plus b to the 2n, all the way to the power of k. And this is our value of n. So after much computation, we reduced n to an easily tackleable sum. But we can't directly evaluate this sum because it's kind of ugly. But we do know that m, by very similar logic, is equal to the sum of b1 all the way to bn inside negative 1, 1 of still b1, b2 all the way to bn, but this time b1 plus b2 plus all the way to plus bn to the k. So these are our values of n and m. We will be looking at how to evaluate n because evaluating n feels pretty simple in the sense, but evaluating n does not. So we will be focusing on evaluating n and relating that to the value of n. Now, how can we evaluate this sum? Well, a good idea is to split things up based on the sum b1 plus b2 plus all the way to plus b2n all the way to the k. Because when we fix this sum and consider the sum of all of these coefficients, then we get something times a to the k plus so on and so forth. So suppose that like c of these guys are equal to minus 1 and the others are equal to plus 1. So c are minus 1 and 2n minus c are plus 1. So that the sum is 2n minus 2c. Then we have a bunch of minus 1s and then a bunch of 1s. And we have a divider line between the first n and the last n. Now, let's see what happens when we look at the corresponding positions. And some motivation to do this is that we have n and n here, so it would make sense to match them up because we are only looking at the first n, so might as well just look at the last n. If these guys are different here, these positions, then why not just swap them? Then we get this one here. Then we get the same sum, but we just negated that. So we just paired everything up, and that just makes cancellation. So the only case we need to consider is where all of these guys are equal. So that means that we also need this guy, this guy, this guy, this guy, and that. So in other words, we need bn plus 1 b to equal b1, and so on and so forth, all the way to b2n equals bn. And this allows us to simplify our sum even further to the following. We get n equals the sum from b1 all the way to bn in -1, 1 of b1, b2 all the way to bn of then because bn plus 1 and all the way to b2n are just b1 all the way to bn, because otherwise we get lots of cancellation by our involution type of thing, we get that this is 2 times b1 plus b2 plus all the way to plus b2n, bn, then this is all to the power of k, and this is all over to the 2n. And we can get rid of this power of 2 and bring it to the denominator. And when we do that, we get that this is b1 plus all the way to plus bn to the k over this to the n minus k. And notice that this highly resembles m, because recall that m is just this exact same thing, but with 2 to the n on bottom. So this is just m times the value 2 to the k minus n. Because by multiplying by k 2 to the k minus n, we multiply the denominator by n minus k, 2 to the n minus k. And that makes it 2 to the n plus n minus k, which is just this. And therefore, this gives us our final answer. N over m equals 2 to the k minus n. And that's the answer to our problem. So what's our main takeaway from this problem? Well, in this problem, we took many, many huge leaps of faith, especially the one regarding generating functions. So that brings us to one main takeaway from this problem, and it's probably the most important one, is to get familiar with generating functions. And by getting familiar with generating functions, we can evaluate so many different cool things, such as the multinomial sum, as we did in this problem, or even in general roots of unity filter stuff, like n choose 0 plus n choose 3 plus so on and so forth. See if you can figure out how to do this one, and I'll leave it up to you to figure it out. And yeah, and another thing is to see how to simplify sums with involutions. Because if we simplify sum with an involution, then a lot of terms just vanish and we only need to consider the fixed points, just like we did when we considered the sum for n. And the fixed points only left the expression for n, basically, minus some constants, which yielded the answer. So those are our two main takeaways. So thank you so much for watching this video, and I'll see you guys tomorrow for the finale of the series.